Hello, am I audible?
Yes, I can hear you.
Okay. Saket sir, I was told that whoever needs to present their screen, just tell me, I'll make that particular person the presenter.
Okay,
Or if someone needs to be converted to panelist, I'll do that too.
okay.
Yeah, that's it. Just tell me when to start and I'll start the proceedings.
Yeah, so I'm guessing that the authors, the presenters will sign in a bit, and I'm guessing that we'll just go with the order in which the website has, right? So Rohit
Yeah.
will probably start. So
Yeah, no issues, no issues. As and when the need be, just tell me and I'll do the required things.
okay, sure. So yeah,
I'm Pratish, by the way, Pratish Wadhwa.
Pritish. Okay, sure. Thanks.
Okay.
Okay, hi everyone. So we have about 5 minutes before we begin the first talk. I don't know if all the speakers, all the presenters are here. I can see Anil and Ankita. Maybe we'll wait for a couple of more minutes. Okay, so I think all the presenters are here. Welcome everyone for the afternoon session. This is session 5, invited papers, 3 deep learning based analysis. So welcome. I hope you have had an interesting day with a lot of exciting talks. And we have 3 talks here today. I am Saket Anand and I am chairing this session. And the first talk is going to be on the paper titled Unraveling Small Sample Size Problems in the Deep Learning World. And it is authored by Rohit Keshari, Soumyadeep Ghosh, Sahib Chhabra, Mayank Watts, and Richa Singh. And the presenter today for this particular talk is going to be Professor Mayank Watts. He's a professor at IIT Jodhpur, and he's an expert in biometrics and AI in general. So over to you, Mayank. And Pritesh, can you please transfer the control to Mayank so that he can share his screen and set up? Thank you.
Thank you, Saket. I would like to just, I don't know how to actually share the screen here. Because, I know how to use WebEx, but I'm not able to see that share screen option.
So I think it would probably be disabled. Pritesh, are you there? Can you hear me?
Yes, sir. I have made him the presenter.
Okay. So Mayank, does it look like the share content button is enabled?
The option should be at the very bottom, right?
Next to start video.
Right next to right next to the start video option.
Right. So it's still not enabled. Let's just try. It's not enabled somehow.
Just give me a minute. Let's check it.
Okay. No, so now this has made me the presenter. So Pritesh, my share content button has been enabled. It's not again disabled. Okay.
Maybe I'll just rejoin. Give me a second. I'll rejoin so that hopefully by that time it will look. It happens with WebEx sometimes. Just give me a second.
Okay.
Saket said, when I transferred the control to you, did your share screen button became?
Yes. It became enabled. Now it's again disabled.
Yeah, I just did that for checking the things, whether the things are all right from my end.
Okay. So let's wait for Mayank to join again. So sorry about the teething issues. Hopefully this will be resolved soon, and I'm sure we're in for an exciting talk. So Mayank, are you able to see the share screen button now? I mean, is it enabled? Okay, awesome, great. So again, thank you, Mayank. We look forward to hearing you. So Mayank, you're not audible. At least you're not audible to me. I don't know if others can.
No, even I cannot hear.
Is this okay now?
Yes.
Yeah, perfect.
Okay. Um, okay, so let me start again. Probably I don't know what happened. Now I'm not able.
Yeah, that'll be great. Yeah.
So welcome all. Welcome for this afternoon session on invited papers. Thanks Raji for inviting us to be here today in the Big MM conference. This work is by Rohit, Somadeep, and Sahib, in which we are trying to understand how deep learning can be applied for small sample size problems. So if we say that we are in a deep learning world, that's not actually an overstatement. We are seeing that deep learning is omnipresent. And when we say AI, we actually mean inherently as a researcher at the back end, we mean DL, like deep learning, right? And one of the popular deep learning techniques is CNN, which we are going to talk about today in the session. But so we can safely say that deep learning is omnipresent, and we are in a deep learning world. There are two keywords in this particular growth. One is the convolutional neural network, the way actually different architectures have been proposed, the way different theories are now actually evolving, or approaches are being proposed to ensure that better representations are extracted and utilized. And the second and a major keyword is data. With the availability of humongous amount of data, progress that has happened in sensor technology, the progress which has happened computational technology, like advent of GPU and all, capturing of data and processing of data has become easy and unviable, and therefore the expressive power of convolutional neural network has actually has multifold increased. So we can safely say that if we have huge amount of data available for a given problem statement, we will find a deep learning architecture which would give us the state of art performance. In old days, like when I started my PhD, we used to say that okay, in computer vision you have to think about feature space and so on and so forth. Now you have to think about deep learning architecture. Probably none of those statements, when I started my PhD, may not hold exactly true in the deep learning world. But now we have to worry more about how deep learning architectures can be trained and newer architectures can be designed, which are safe, ethically viable, and robust and accurate. However, what about these small sample size problems? So first of all, to understand what do we mean by small sample size problems. So if I have a rare disease, if I have something for which in the entire world there are barely, let's say, 1,000 patients, how can we actually use AI for detecting such diseases? If you're thinking of image captioning problem, while we can have image captions for traditional like sky images or aeroplane images and so on and so forth, but the instances for an airplane crashing may be very limited, very few. So how image captioning algorithm would visualize a crashing airplane? Can actually, it understands that it's not actually a plane parked on a tarmac. Actually, it's a plane which is crashing. In fact, there was a in recent flood in Bihar, when automatic algorithms were trying to, like, when people ran the automatic algorithms to understand what kind of captions it would generate, it was generating actually people staying in beaches. So that kind of instances are algorithms are equipped with, and those are small sample size problems where for the training purposes we may have very few samples, but for the testing purposes we may have good amount of data to test, right? So when we say a small sample size problem, it's inherently we mean that the training data is very limited. Another interesting example on which students have worked on in past is like face recognition or children's. For adult faces, we may have a lot of training data, but for newborns, we have very few training data. And the variability that actually the faces show when the baby, let's say when 8 months old, that kind of variability is not available in any of the data sets available in the research community. And That's why we actually call them, and the kind of expressive power these babies have with respect to their laugh, cry, and so on and so forth. They are essentially unintentional, non-cooperative users for the system, and that no database exists which covers all the variability which the newborn face recognition algorithm could understand. And therefore, this problem can be easily classified into a small sample size problem where the biggest database available for conducting research has training samples belonging to only 90, and that is from our group. There is no other data set beyond that. So now how do you train a face recognition algorithm for performing this particular task? We have shown that means an algorithm which is which shows over 90% accuracy on adult face recognition shows barely 30% on newborn. A fine-tuned VGG face barely shows actually a fine-tune on these 90 babies and tested on another 100 babies showed barely 60% accuracy. So this shows that there is a real-time or a real-world requirement of small samples, solving a small sample size problem. Here is another example. Anyone actually can try. Who is he? Saket, can you try? Rajiv, if you're there.
Isn't you?
Yeah.
Not really.
So I was actually about to guess that, but yeah.
Okay. You have a small sample size trained deep learning model running on a brain, so that's really good. So a human brain is pretty interesting. It does a lot of samples, but some context is required. So kinship analysis is another important application for law enforcement applications. When have one kin's image, can I generate the second kin's image, or can I actually figure out who would be the second kin? Think about this Boston bombing case where two brothers actually were involved in Boston bombing, and in different videos, these two brothers were actually observed. Had we actually known that these two are brothers, investigation officers would have actually expedited the whole process of capturing both of them. So for this kind of research also, we have very limited training. Not everyone has brothers or sisters, or the data for this kind of research that is available is also very limited. And another interesting problem which some of our students started working on is malnourishment detection in babies. Again, a problem which is of social interest, but that availability of training samples is negligible, actually nil. When we started working on this, there was not a single data set. As part of our research, we are now releasing the first ever data set to perform malnourishment versus healthy classification, which has a data set of barely 3,000 babies. So from deep learning perspective, all these are small sample size problems. Now, how to perform classification, how to perform this deep learning based learning on small sample size problems, right? So then there are several examples in the Indian context, and then we can very safely say for one problem with large training data, there are 1,000 small training data. And the question is that how do we apply deep learning or CNNs for those applications? So if you look at any traditional CNN architecture, so some of you may think that what's the big deal about this problem? I can take a pre-trained model, and let's say pre-trained on ImageNet, and I can fine-tune the last few layers, or even if we have sufficiently decent sized data, we can fine-tune few more weights, like last few con layer weights, just not the FC and softmax. You can fine-tune, and then test on small sample data. What's the big problem? But the problem actually comes in when the samples are very few, and kind of filters that we are observing on, let's say in this example, regular adult faces may not fit well for another problem statement, or target problem statement, in this example, newborn face data set. So these filters would not be, even after update, the samples are so few that these filters will still not be able to perform accurate newborn classification. And as we've shown earlier, that even a fine-tuned VGG would show only 60% accuracy, whereas the VGG face recognition model shows over 90% accuracy on LFW dataset. Right. So this kind of traditional domain adaptation transfer learning technique by fine tuning does not work in most of the small sample size problems. So in literature, if I look at all the small sample size problem approaches, they can be classified into broadly 3 categories: input space, model space, and feature space. I'll quickly go over each of these to give you an overview of like what happens in these spaces. So if we look at input space, techniques like data augmentation, image-to-image translation, adversarial learning, or data augmentation using pixelation or blurring, or more recent zero-shot learning techniques have been proposed. In model space, when we look at the cost function. We add a regularizer, which is domain-specific regularizer, and by incorporating by cost and incorporating some information as a regularizer, which is domain-specific, can help the model to learn better and faster. In our CVPR 2018. From the simple adaptation, like simple transfer learning or simple fine tuning, we have proposed that if we can learn the structure and strength from small sample size. So given a pre-trained filter from, let's say, adult faces, how can we actually adapt these filters locally using the small sample size data set and attune the filters on these small sample size data sets only? So not training the entire, like all the weights or just a FC layer, just start looking at individual filters using some cost-effective tricks. Can we actually update the CNN architecture? And that's what we proposed in CVPR 2018, where we proposed structure and strength based convolutional neural network, in which the CNN was trained, the filters were primarily trained using a large phase data set, and then these were updated based on small samples. And then the idea was very neat. The idea was that once we have trained the network, we freeze those filters, which are trained on large samples, but we train the strength of each filter separately on small sample size data. So if my convolution layer, one layer has, let's say, 8 × 3 × 3, that's the size of my weight matrix. On the small sample size data, we are going to only train or obtain only the strength parameter, and which will be only the number of filters in that particular layer. So we have significantly reduced the number of parameters to be trained on a small sample size, and therefore we can avoid overfitting. The third category is feature space, where we can learn the features better for small sample size problem. And then triplet loss has been actually used and actually suggested that even if you have as low as 100 samples or 200 samples, you can create thousands of triplets based on these 100 samples, and that can actually work with that can actually work to reduce intra-class variations and increase your inter-class variations. Right. So the classical inter-class and intra-class optimization can be worked on using triplet loss. And recently in 2020, early 2020, we proposed another approach. We called it a shield approach, where how to actually train, which is based on the quadruplet loss, in which we said like how to actually train the network with more variability and then have a compact clusters for different, and then push away different clusters of different other classes, so that the training is better. In this particular paper, if you look at the way actually we have proposed briefly a new technique called dynamic attention pooling. Traditionally, when we look at global average pooling, it performs average complete feature map. And it actually, our observation is that it reduces the intensity of the feature. To avoid that, we have proposed this dynamic attention pooling, which works on small windows and traverses the entire feature map, and then actually seeks the maximum attention, which helps in improving the classification performance. So on 4 different data sets like CFAR 100, CFAR 10, SVHN, and Tiny ImageNet, we observed that on a ResNet architecture with the traditional GAP and GMP, and a combination of GMP and GAP. Our approach, like dynamic attention pooling, even as simple as a small update of attention pooling, shows improved performance. So with this, I would like to quickly summarize that while it's good that we all are trying to solve problems of large where the large data sets are available, but at least in Indian context, we need to ensure that we are also solving small sample size problems, and our effort is in those directions. And then hopefully some of the audiences over here also would take that forward. And I would acknowledge the IAB lab students who have been contributing in these efforts. Thank you very much.
Thank you, Mayank. Thank you very much for the very interesting talk. That's a lot of work. I would request the audience, if there are any questions, we can still take, we have a few minutes before we get started with the next one. So if there are questions, please feel free to unmute yourself and ask.
Okay, so probably I can ask one question. So it's a really very nice work, Mac, and I also agree. Like the scarcity of the data set for Indian faces are it is there, and so but still, I mean, could you highlight probably to the, I mean, the community, or especially the young student who are working, who can take the work forward, some of the data set for the Indian faces, which is, I understand, maybe not be too big, but should be fairly well.
So there are actually about sets that we have prepared from different perspectives for different problem statements, including the newborn ones. We have prepared, and those are available for anyone to download and do research on. So that's certainly there. In India, actually, okay, so Indian users generally are the consumers of data, not the creators of data. So probably that's another important message for the young students over here in the audience, that if you are looking at some problem statements, it is worth considering like spending some time on creating some data sets on your own. You're also showing results on some existing data sets. So at least some of the data sets which are available from our group are available on our website, and then they can download. But not very many databases are available from Indian context.
So based on your experience, what are, do you think the facial attribute might be very, very useful in case of biometric?
Okay. If I'm looking at, let's say, gender analysis, then we have actually shown an interesting observation in one of our that in order to classify, let's say, male versus female, some of the ornaments, as simple as even a bindi on the forehead, can help classifying a male with female. So there are some specific Indian specific things which there, but end of the day, a face is a face means, but the structural variations on which the data needs to be trained on, mostly the major distribution should remain same, but these are like external factors which may be there, which needs to be incorporated. Because end of the day, like a bindi on a forehead for an Indian woman is a common feature. Probably 50% of Indian women actually wear that. So if the algorithm sees this as a feature, then you will observe that. So there are like some subtle variations also, but it's not that these are very specific to only Indian faces per se. But yeah, I mean, as I said, like there are some external factors which may play a role in differentiating an Indian face with others. But as I said, like there are like the data distribution belonging to Indian versus a data distribution belonging to Western population, or let's say, Asian countries and other countries may vary. The mu and sigma may vary, and there is no closed form answer that this is how an Indian face would be defined, and we cannot define the same, let's say, Western, like African American or Asian faces.
Okay, thanks.
Okay, I think we are also out of time, so maybe we can move on to the next presentation.
Thank you, sir. Thank you, Rajiv.
Thanks a lot, Mayank. Yeah, so I second Mayank's recommendation of generating data. We should be collecting more data, and because we have a lot of interesting data around us as well. But yeah, so coming back to our next presenter, Anil Sharma is already here, I think, and he will be presenting his work on stratified sampling-based experience replay for efficient camera selection decisions. And his co-authors are Mayank Kumar Pal, Saket Dsme, and Sanjit Kaul from IIIT Delhi. So Pritesh, can you please hand over this, the screen sharing ability to Anil?
Yes, sir. I've done the needful.
Okay, thank you. So Anil, you can get started, please.
Okay, I'm just sharing the presentation.
Okay, great. We can see that now.
Hi everyone, I will be presenting our work titled Stratified Sampling Based Experience Replay for Efficient Camera Selection Decisions. Camera networks are becoming ubiquitous and there are many potential applications. For example, traffic flow analysis, where the task is to track a particular vehicle across multiple cameras that are installed on different road segments for collision avoidance at intersections, or to identify the travel time of individual road segment. Another potential application is monitoring and surveillance, where the task is to track a particular person in the multiple cameras installed in a building. So for target tracking in a camera network, we are given with n camera streams, and we have to determine the target's position for all times in all the cameras. We are also given with the initial location of the target at the starting frame, which is C, B, where C is the camera index and B is the corresponding bounding box in camera C. The output of the tracking algorithm in this case is the estimate of the position of the target for all subsequent time frames in all the cameras. The existing approaches for tracking in camera networks follow a two-step approach, where the first step is SCT, which is single camera tracking, and second is ICT, inter-camera tracking. In the first step, the individual tracklets of all the targets are meshed together using visual data association to form the single camera trajectories of all the targets. In the second step, these single camera trajectories are meshed with each other, again using visual data association to form the multi-camera trajectories of all the targets. In these methods, this visual data association method is often area identification based method. So if we look into the ICT part, let's say we are given with the trajectory of the target in camera 1, and the target exits this camera field of view at time t1. Then a typical tracking algorithm starts searching for the target in all the cameras at all the times to find the target. Let's say after time t1 plus t prime, the target is found in camera 2. Then using visual data association, the previous trajectory of the target is merged with the new trajectory to form the complete trajectory. These approaches largely focus on visual data association, and they query even during the blind spots, which results in redundant query. So to make target tracking efficient in camera networks, we need to answer a few questions like how often do we need to query when the target is transitioning between cameras, and which camera shall we query? For this, let us see camera selection decisions. Let's say we are given with the initial position of the target at time 1 in camera C, I. And at time 4, the target exits this camera field of view. So now, to predict the next position of the target, we first need to decide whether we need to query a camera or not to query, because the target may be maneuvering between the cameras. That's at time 5, we decide not to query. CX represents an action where we decide not to query any camera. Same at time 6. And after time tau, let's say we decide to query a camera. Now, in which camera the target is most likely to appear? So let's say we plan to query camera CJ, then we will be making a re-identification query to identify the location of the target so that we can continue with the trade. Now, since at every point in time, here we are making a sequential decision to select cameras. So we are formulating this problem as a sequential decision problem, and we are learning a policy using reinforcement. So in this direction, our contribution is that we have proposed a method, certified sampling in experience replay, to learn a policy using deep Q learning. It solves the sample imbalance problem in experience replay that we will be talking in one of the future slides. For performance evaluation, we will be using NLPR, MCT, and Duke MTMC dataset. NLPR dataset has 4 sub-datasets. Each of these datasets have different number of cameras, and there are significantly high number of people in each dataset. And this image shows the 8 cameras of Duke MTMC dataset, which are installed in Duke University campus. To formulate the problem, we have used Markov decision process, which is a tuple of 5 elements. The first is state vector, which contains the observation C, B, which is the camera and the corresponding bounding box of the target's location, and the information tau, which is the time elapsed since the target was last spotted, and the camera history HT, which is the history of cameras queried by the policy, and this is our final state vector. The action space A is encoded by an n+1 dimension vector, where n is the number of cameras. So for example, if the policy decides to query camera 2, then it will be selecting action 2. If it decides not to query any camera, so it will be selecting n+1 of action, which is represented by CX. For policy learning, we have defined a reward function R for each state and action pair, where Y is the ground truth camera and A is the selected camera. We have given a positive reward when the selected camera and the ground truth camera are equal. Otherwise, we have given a negative. We give a minimal positive reward for the case when the selected camera belongs to CX, which is one of the frequent action in our action space. We have given a small positive reward for the cases when the transitions are short and easy. The high positive reward is given when the transitions are long and rare. We have used state action value functions QS, A to estimate the average future reward of an action A for the given state S. The optimal Q function Q star is learned iteratively using Q learning, and an optimal policy pi selects an action A from these optimal Q functions using this equation. So we have used deep learning to approximate these Q value functions, and this is the network architecture. So to learn a policy, we first create an initial state of the target from the multi-camera stream from the target's location, and we initialize tau and st as zeros. And a neural network is used to approximate the Q values. The policy selects an action which has the maximum Q value. In deep Q learning, the transitions from the neural network are stored in a replay buffer, so that later in time we can sample transitions from the replay memory which are not correlated, and we can compute a loss which we can propagate to the network to compute the optimal weights. This process in DQN is also known as experience replay. Sampling in experience replay is highly important and impacts the performance. So for example, uniform sampling is one of the common method for sampling from the replay memory. So first, let's just consider this figure, which contains a sequence of cameras in a trajectory of one of the target from dataset 4. It contains 2 sequences, a ground truth sequence of cameras and selected sequence of cameras from the policy. So each color represents a camera field of view, and the white space between each color represents that the target was transitioning between two cameras for this period of time. So we can see that the transition time is very large as compared to the time the target was staying in a camera. So if we are using uniform sampling from the experience replay, our policy is selecting the most frequent action CX and is not able to capture most of the transitions that the target followed. Another approach for sampling in experience replay is prioritized sampling, which is also known as prioritized experience replay, which assigns a probability with each transition, and this probability is decided by the loss of the neural network. If we are using this kind of sampling, then also we are not able to capture most of the transitions, and the policy's decision is biased to the most frequent action. One of the recent approaches is experience replay optimization, which instead of assigning a probability, they propose that we can learn a policy to decide which transitions to sample from the replay memory. So even this kind of method is not effective to capture all the transitions from the trajectory, and it is also biased to the most frequent action. To analyze why this is happening, we have analyzed the different actions that are present in the replay memory. So here the replay memory size is 1 million, and there are 3 lines here. Each color line represents a different place, where green line represents the transitions which contains the frequent action CX. The magenta line shows the transitions which contains which ended in a negative reward, and the blue line represents the transitions which ended in a positive reward. So we can see that the number of samples of these transitions are highly varied. So here, like when the replay memory was filled at this point of time, so the around 9 lakh sample were of the transitions which were in CX, and around 1 lakh from the other two. So that means here the replay is highly dominated by the most frequent action, and hence this could be one possible reason for the like poor performance of those methods. So to analyze it further, we have seen the different actions in the sampled mini batch of different approaches. For example, PER, uniform sampling, and ERO on DB3. And we can see that PER is relatively good in terms of the diversity of the mini batch at some point of time in the training. But uniform and ERO are highly dominated by the most frequent action CX. Whereas the PR, which was performing relatively good on DB3, is also performing poorly on DB4. So that means the mini batch that is created by these methods has more samples of the frequent action, and hence the neural network is not learning a good policy. So our goal here is to make a diverse mini batch with all kinds of rewards, so that we can learn an optimal policy, and so that we can capture all the transitions. So to achieve this, we have proposed stratified experience replay. In this, what we are doing is we are dividing our replay memory into multiple parts, RF, R negative, and R positive, where RF will store the transitions that correspond to the most frequent action CX, and R negative will contain transitions which ended in negative reward. R positive will contain the transition which ended in positive reward. So during like when mini batch creation, we will sample transitions from each of these replay memories equally, and then the final mini batch will be the union of the 3 batches that we have sampled. So this is the full working of the stratified experience replay, where from the agent environment interaction, the experience of the transition that will come up will be stored in one of the replay memory based on the reward that this experience of the transition receives. And when we are sampling from these replay memories to create a mini batch for backpropagation, we will be taking equal number of samples from all replay memories, and we will be sampling uniformly from RF and R negative, and R positive is an prioritized sampling because there are rare and like easy transitions in this replay memory. So this is the camera selection performance of different RL approaches on one of the trajectory in our dataset. So PPO is one of the reinforcement learning method which doesn't require replay memory, and we can see that even this method is highly biased to the most frequent action CX. We have talked about PER, uniform, and ER, which were taking decisions more towards the frequent action. And SER is our proposed method, and we can see that when we are using a stratified sampling from experience replay, we are creating a good mini batch, and the neural network is able to learn a good policy, and most of the cameras are captured by this method. To quantify the camera selection performance, we have used accuracy, precision, and recall metric. To compute the accuracy, let's just consider two camera sequences, G and P. G is the download sequence of cameras, P is the predicted sequence of cameras. Each color represents a camera field of view, and cross represents that this is the transition time. To compute accuracy, we will count how many of times these numbers are matching. So in this case, it is 10 out of 15. And to compute precision, we will see how many of the predicted cameras are actually correct. In this case, it is coming out to be 6 out of 10. To compute recall, we will see how many of the actual download cameras are recalled correctly by the policy. And to quantify the computational performance, we have defined a number of frames processed metric, and in this we will count the number of spurious re-identification queries made. So it will contain both the extra queries made and the wrong queries made to the network. So the lower this number, the better it is. So this formula is used to compute this metric. And these two tables shows the camera selection performance on two datasets, NLPR DB3 and Duke MDMC dataset. We have included comparison with most of the reinforcement learning method, and also CAMCEL and NCEPs, which are state-of-the-art methods for camera selections in camera networks. And we are like better than most of these methods on at least two metrics. So this figure shows the number of re-identification queries made to the camera network. This is computed using the F metric that we have described in one of the previous slides. Here we are making comparison with two baseline methods, exhaustive and neighbor, where exhaustive means that we are exhaustively querying a camera network, and neighbor means that we already know the camera network topology and we are only querying the neighboring cameras. Gaussian is an intelligent approach where we are learning the transition time using Gaussian distribution, and we are sampling a transition time from this Gaussian distribution to identify the time where we don't have to query. And this is the NCEPs is one of the state-of-the-art method for camera selections. We can see that R and select is R method, and this makes a very few number of spurious re-identification queries to the camera network as compared to other methods. More qualitative and quantitative results of our method are reported in our paper. So if you please go to the web page and look into the paper for more results. Thank you for your time.
Thank you very much, Anil, for the presentation. If there are questions, please kindly unmute yourself and ask a question. Thank you.
So, Anil, this is Mayank. Just a quick question. This problem does this problem require an RL approach? Can we solve this problem using a non-RL approach? And if yes, then what is the benefit of an RL approach?
So yes, this can also be solved using non-RL approach, and there are many methods using that. But RL has an inherent advantage. So for example, like here we have included a reward function, like which is taken from the ground truth. But this can also be modeled using some like existing approaches like re-identification based approaches, and this can be made totally unsupervised. And second advantage is that here we don't need any assumption of the camera network topology. So for example, other methods require to identify like we need to identify where the target is moving and which are the linked cameras. But here we don't need to have any kind of information about the camera network topology, and it can work independent of that kind of information.
See, my question was because of the slide only, because we are using inherently you're using ground truth.
Yes.
So if you're using ground truth, at least in a classical way, this does not look like a pure RL approach, right? And then if you are using ground truth, then probably why not actually use it to the full extent?
So basically, it is not like completely like using the ground truth, but it is like it is making only like it is using ground truth only for the cases where the policies like on the policy's decision. So basically, if your selection is correct or not correct. So like that kind of approach. So basically, like, so yes, we have used a ground truth, but in our future work, we are planning to like make it is unsupervised and replacing this reward with the other available approaches, and we are currently exploring that.
Sure. Okay, thanks.
So, just to add to that, I mean, usually the rewards can be noisy. So, if technically, you could make it. I mean, you could take a self-supervised, not a self-supervised, but a supervised re-identification algorithm and use that instead of the reward. So it could. I mean, if it is even if the re-identification method makes errors, you get a noisy reward, but most of the advantages of training an RL agent would still hold there. So,
Right.
so
So
in
no,
that
I agree that
sense,
when the advantage of RL is there, but then so the moment actually we start using the ground truth, so in true sense, it's
right,
no more an RL. So
right. So here the purpose of using the ground truth was to validate whether an RL approach would work here or not, because seemingly it was a sequential decision-making problem, because at every time step you are deciding whether or not to query and which camera to query. The other thing is that this transition time varies a lot across pairs of cameras, and
Right.
also for different targets it might be different. So then there are papers which have a stationary distribution which they use to model the transition time, but then in reality these distributions are not necessarily stationary. But if we use RL, then this non-stationarity can be handled a little bit better. It doesn't necessarily completely resolve it, but it might be better. It's better than just assuming stationarity there.
Yeah, sure. Thanks, Saket. Thanks, Anil.
Okay, so I think we are also out of time. So Anil, thank you very much for the presentation, and maybe you can disable your screen. Yeah, thanks. And we have the next speaker, which is Ankita Shukla. So she is going to be presenting her work on semi-supervised clustering with neural networks. This is again with collaborators Bilal Singh Cheema, who was at IIIT a few years ago, and again me, Saket Anand. So Ankita, can you please try to share your screen? Okay, great. Thank you.
Am I audible? Hello?
Yes, you are. Yes, you are.
Okay. Hello, everyone. So I'll be talking about our work on semi-supervised clustering with neural networks. Here's a brief overview of what I'll be talking about. I'll be first discussing why we need deep clustering in the very first place, and then some of the recent developments in that direction in the past couple of years, followed by the proposed formulation and some results on image datasets. So as we all know, deep neural networks have achieved state-of-the-art results on various supervised learning problems, whether it's object detection or classification, because of their capability to use large amount of label data. However, there's still a problem when we want to use these approaches for novel applications where you do not have large amount of label data or no label data at all. In that case, one can think of using clustering approaches where one can group the data or organize the data based on some sort of semantic similarity. So in classical sense, k-means is one of the earlier algorithms which can be used for clustering, which has two important components. One is how you represent your image data, and second is this metric that you use to drive the clustering process. So in these classical settings, we often have the problem of fixed representations because these are defined as some low-level features that you extract from your images, and most often but not, you use simple matrices, metric like Euclidean distance or a cosine similarity. But with the success of deep neural networks, there's a possibility of using deep networks for clustering applications as well, where we can use the expressive power of deep networks to learn these representations, which are clusterable in nature. So in order for a deep neural network to do good in clustering, you would need two components. One is the constraint, or the way how you're going to define that these two images are similar or dissimilar, and an objective function to enforce the network to learn such kind of constraints. So existing work in the literature could be categorized based on the level of supervision people have used in developing these techniques. So the first is the supervised clustering approach, which is essentially a specialized form of a classification problem, where all the data has all the pairwise relationship between the data is defined, and that is used to drive the clustering. So which eventually fails the purpose of saying that you do not have labeled data at all. And the second is the unsupervised clustering, which is the other end of the spectrum, where you do not make use of any unlabeled data, but that can fail in capturing any sort of semantic information that you're looking for grouping the objects. So more recently, there is more trend and work of semi-supervised clustering, which could essentially be seen as a version of unsupervised clustering, where you have objective function that you're trying to minimize, where you which can help you cluster the representation, but at the same time you have another auxiliary or a pretext task which is just there to support in the process of generating these semantic representations. But the problem with these self-supervised clustering approaches is that they're very high on compute. For example, the Key et al. 2020 paper, which came out in CVPR, requires around 64 GPUs for 6 days on one of the data sets, and similar other requirements have been presented in other work that have been proposed. So now I'll come to the semi-supervised clustering. That is what I'll be talking about. But in space, there is not much work has been done. There was one or two papers that came out in 2015 and 2018, but they lagged in the way of utilizing the unlabeled data efficiently. For example, the work by Kira in 2015 only utilized a small percentage of labeled data and did not account for any unlabeled data, which could be very well used for driving the representations to be better clusterable. So here I'll talk about how is our approach is a movement in that direction, because we propose a single end-to-end network training, which can learn clusterable representation without the need for huge amount of compute. So it is an autoencoder based framework and makes use of both labeled as well as unlabeled data. And the loss function basically has three components, which efficiently utilizes both labeled as well as unlabeled data. The first is the constraint k-means, which is used by the labeled samples for guiding the clustering. I'll discuss it in more detail in the coming slide. And the second is the pairwise scale divergence term, which is defined on the unlabeled data as well as the labeled data, but is essentially there to help one to label the generate pseudo labels for the unlabeled data. And third is the reconstruction loss of the autoencoder, which ensures that the learned representation space is not degenerate. So the first component, the constraint k-means, it was an earlier approach proposed in 2002, which essentially aimed to improve what k-means clustering does by adding certain amount of labeled data in doing the cluster center initialization. Instead of doing random initialization, you use your label data to initialize the cluster center. And with every iteration, you assign labels to the unlabeled data, while you do not change the labeling for the labeled data points. In that case, it has been shown that it can improve the performance even with as less as 2% of labeled data. So that is one component. The other component is the pairwise scale divergence. So this is a crucial component which allows us to leverage the unlabeled data properly. So given the set of data points and unlabeled data points, and we have a cluster assignment, we want that similar point should have a similar way of getting distributed along different clusters. So in a way, if I have class probabilities vectors corresponding to two samples and they belong to the same cluster, provided I know that, then I would want that their distribution should be very much similar, or their divergence between their distribution should be smaller, and it should be the other way around for dissimilar pairs. So considering these 2 points, these two components, the objective function for our approach could be written as follows, where small l subscript is denoting the component corresponding to labeled samples, and small u subscript is denoting components corresponding to dissimilar, corresponding to unlabeled samples. And recon is the reconstruction loss. Here you see a parameter lambda in front of unlabeled samples. So this is a parameter which evolves during training based on the level of confidence that we have gained already. And so that when you start using unlabeled data, it should be making a effort in the positive direction and learning the representation instead of reducing the performance. So here are some of the notations that I'll be using in a couple of slides. You don't have to really understand them. So here, so F is for encoder, G is for the decoder parameters. Sorry, there's a typo here. And then I'm using similar and dissimilar pairs in the calligraphic T with U and LS subscript for unlabeled and labeled data sets respectively. I'll discuss the rest as they come in the slides. So the loss function for the labeled pairs could be very easily just written as the distance from the cluster center. So the L cluster is essentially just that you want to cluster the point, a labeled sample X corresponding to the cluster center from where it arises. And similarly, you can write the pairwise constraint or the KL divergence term over the similar and dissimilar pairs here, where you are trying to say that for the points which have which belong to the same class, or because you have label information, you want to have the divergence smaller, whereas you want to increase the divergence for dissimilar pair. But here, one has to note that one is using the label information to define these two losses. Whereas in case of unlabeled data, you can use the intermediate network predictions to find a pseudo label, which could be used to define these losses. So similarly, you can define the pairwise loss for unlabeled and the cluster loss for the unlabeled data. So considering these four loss functions, the optimization strategies goes as follows. You initialize the cluster centers with your limited label data, and then you do cluster assignments. Now, when you're doing cluster assignments, you don't have to do cluster assignments for label data, and you can just update the cluster assignment for unlabeled data based on the cluster center, which is the nearest to it, and assign that it as a pseudo label. And then you create your similar and dissimilar pairs using these label assignments for unlabeled data. For label data, that is already defined. And once you have defined that, again, you want to update your understanding of the representation space. So you do a update of the assignment probabilities, that given a sample, what is the probability of it getting assigned to different clusters? So which could be again obtained using just the distances and then converting into a probability measure. So using these updates, and now we can update the cluster centers with a simple equation which comes out because we had L2 norm term over there. So the cluster center update is a very simple equation for unlabeled as well as for labeled samples. Here NKL and NKU are the samples which have already been clustered in a particular cluster center that we're talking about. And with all these updates, you do the normal back propagation of your network to update the encoder and the decoder. So that is a brief overview of the optimization strategy. And the important component here, which still remains, is the lambda, which is the annealing strategy, which will start counting into, which will give weight to the unlabeled data based on their confidence of how well they have been doing so far. So here we use lambda. We do not use unlabeled data initially for certain iterations because the network has still not understood uh, uh, these kind of unlabeled data sets. So after certain iteration, you start weighing them slightly, and after another threshold T2, you can start using them uh, uh, at a, like in the similar fashion as you were using the label data. So these values T1 and T2 were fixed for all our experiments, and we experimented a little bit around these, but it kind of worked for all the data sets that we have shown in this paper. So we use two evaluation metric to evaluate the performance of our approach, the normalized mutual information, which is a standard metric used for computing the clustering performance, and the classification accuracy, which is computed using the pseudo labels that we get from the unlabeled data. Here are some of the data sets that we are using in the process. So MNIST and USPS are digits data sets, whereas the rest three are face images data sets. And these are two different tables. The second table is essentially denoting the samples which are completely unseen to the network, even during the network training. So here is a comparison with some of the recent approaches. So DEC, Joule, RC, and DEPIC are entirely unsupervised approaches, but CPAC PGZ is a semi-supervised approach where they use pairwise constraints. And so here is this comparison. The amount of labeled data is given in percentage in each of the rows. So 0.5% of labeled, only 0.5% of the labeled data is used when you are training the network, and the performance is shown in the entire data set you have. So we see a significant boom by just using like this 0.5% of the data for MNIST, but this number could go up to 5% in case of much harder data sets. So here's an example of some of the Dsme plots that you could see on the different percentage of the label data. So this is the original raw data set on the left that you're looking at, and the middle image, the middle figure is just showing when you train the autoencoder and you plot the representations in the same two-dimensional space. And the third figure is when you do the clustering loss, the cluster net that we propose, and you could see the semantic information is making sure that the data gets clustered nicely. Here's another example for different percentage of label data. So 2% label data and 5% on the left and the right respectively for YTF and MNIST data sets. And here, so we wanted to look at if what kind of cluster center is it learning. So we randomly selected a certain set of cluster centers from the representation space and reconstructed those images, and they looked out to be turned out to be the representative of the images that were clustered in that cluster. So that is on the left, and on the right we are just showing the effect of adding the reconstruction loss, which allowed us to ensure that the images indeed are valid images. Because the reconstruction loss is ensuring that the space is not collapsed into just the cluster centers. So more quantitatively, here we are comparing the cluster net if we just do not have a reconstruction loss as opposed to the reconstruction loss. You can see a clear improvement in terms of the performance, both in NMI as well as accuracy scores. And then we also, as we talked in the initially in the very first slide, that organizing the unlabeled data so that it could be used in applications where you do not have access to a lot of training data. So we ended up doing k-means clustering on these representations that you obtain from a normal autoencoder or a autoencoder trained with a cluster net loss. So there we see that the clustering performance has drastically improved for these different data sets. And here we are analyzing the effect of different values of lambda coefficient that we have used. Using a fixed value of lambda will give you suboptimal performance, because if you're using smaller values, you will not be using the potential of the unlabeled data properly. But if you start using it from the very early itself, it will also hamper your performance. So annealing strategies allows you to alter the value of lambda over training, and which ends up helping in boosting the performance in a positive way. Thank you.
Thank you, Ankita. We still have a couple of minutes for a couple of questions. If there are questions, kindly unmute and speak. So any questions from the audience?
Okay, so I think it's not. So I request, since we are waiting for the next session. Okay, so I guess we have one question. So after this question, I request everyone to please join session 6. I have already posted the link. Yeah, so after this question.
Okay, so the question is how to decide how to decide the threshold value when you're doing the labeling. So is this threshold the lambda parameter, or I'm not sure what the threshold value is. Aditya, feel free to unmute yourself and speak if you like.
I'm asking about the threshold value, the lambda parameter. How to choose the lambda parameter for the task?
So we haven't fixed the value of lambda. So we used I can just go back. So it is an adaptive value which changes over iterations.
Okay.
It is not a fixed value. So if you look at the equation here, so initially, because your unlabeled sample has not been seen by the network enough, so you don't want it to affect your embeddings. So you do not want to use it for a certain number of iterations, but that number of iteration is really small here, like five epochs is what we are using here. And after that, you just gradually increase. So this is a linear increase, right? So you keep on increasing the value of lambda by a certain margin here. For example, if you see t minus t1, and so which is a linear increase in a lambda value, and so that it's adaptive to the learning process.
Okay. Thank you.
Okay, great. Thank you very much, Ankita. We are also out of time, so thank you everyone for joining the session. And I hope you found this session interesting. Thank you.